Welcome to the TAS 13 webinar on PV and energy security in the Greater Arctic region. It's my pleasure to organize this webinar, and I would like to introduce myself. My name is Ulrike Jahn. I'm working at Fraunhofer CSP in Germany, and I'm the task manager of IEA PVPS Task 13. Before we are starting with the content, very brief, the International Energy Agency has a technology collaboration program called Photovoltaic Power Systems Program, and it is one of the 38 currently active programs. It was established more than 30 years ago, and it includes more than 28 countries, plus the European Commission and 2 sponsor members. We are 9 active tasks, such as Task 13 on performance and reliability of PV systems and components, as well as 1 action group on agrivoltaics. In this program, Photovoltaic Power Systems Program, we have published 27 reports during the last year, and more than 20 events were organized. And the whole program includes about 400 expert participants working across different countries and all PVPS tasks. And here you see the active countries who are involved in this program, and you can see most continents are covered, some continents more than others. And I would like to go back a little bit in the history of our work program, Task 13 on reliability and performance. We started 2010, collecting data and doing analysis on performance and reliability of PV components and systems, looking also for international testing and standards. Very soon in our second round, we felt it was important to look for yield prediction and to define uncertainties, but also to start looking into specific failures, how to detect them, and to make some overview and assessment for failures in the lab and in the field. In the third phase, we moved downwards towards the operation and maintenance. We were looking for best practice guidelines, how to do quantification and qualification of PV power plants in the field, as well as risk analysis, risk assessment and mitigation, and how to mitigate these risks. In the past phase, which ended end of last year, we looked on material and applications. We also included digitalization and digital twins. We specifically focused our work on design and testing of PV plants and components in different climates and environments, and also developed key performance indicators for different applications. And also 1 group was dealing with PV and battery systems. And this is the focus of our work up to date. So in one of the subtasks, we focus on new PV technologies, their design and their components. We also have a focus on digitalization and AI use, particularly for the downstream applications. We look on inverters and storage systems, and PV application means that we put efforts into floating systems, into soiling, and last but not least in Arctic PV applications. And that is the topic of the webinar now, where you will hear 3 dedicated talks in the next 60 minutes. So why are we doing this webinar? And you can see the reason on the right-hand side. We recently published a report which shows that PV can make a very meaningful contribution to Arctic energy systems with climate-specific design. What does it require? We need solar resource data and albedo data for calculation of the yield. We also need modeling and improved modeling approaches to calculate the snow losses, but also assessments, because we are dealing with permafrost regions. And you will hear much more about this in the next hour. Um, the report also explores the opportunities and very unique challenges in deploying PV systems at high latitudes. Why PV in the Arctic? One number is 17 million people who live above the 90th degree north of the equator. And in many communities, they rely on expensive imported diesel fuel. And there are several challenges with dark winters, with heavy snow loads, high wind loads, extreme cold, then material properties to be leveraged. Also remote locations for shipping, installation, and O&M cost. But there are also advantages of having these north location with low temperatures, which give input to increased cell efficiencies. For the best practice, you will also hear more about the design, and you see examples from Norway and from other locations, and why it is important to take care of the different architecture of these systems at low angles, and that the solar azimuth does have a very large range, and how to deal with the snow impact, and why design aspects play an important role in having a successful operation of PV systems in the Arctic. So if you want to learn more about these deliverables and others, here is the website, and you can also subscribe our newsletters. You can follow us at LinkedIn or X. And just as two other examples, that recently we also published a report on degradation and failure modes of new cell and module technologies. And very soon there will be a second report on the optimization of PV systems for different applications. So feel free to download the reports and get in contact with us. And this is to introduce the speakers you will hear in the next hour. So first of all, Dr. Erin Tonika from Natural Resources Canada. The second talk is prepared by Adam Jensen from the Technical University of Denmark. His presentation will be given by Erin. And last but not least, Dr. Joshua Stein from Sendia Labs in the USA. And with this, I just like to give some words on Erin. She holds a PhD in physics and focus her work on bifacial PV systems, mid to high latitudes. And since 2025, she's working at Natural Resources Canada and leads projects on solar resources, solar monitoring, and technology testing for supporting northern and remote communities. And with this, I would like to hand over and give the floor to Erin, please.
Great, thank you. I'll just start sharing my screen here. Alrighty. Let me get up my laser pointer too. All right, so you should be seeing the first slide here. I'll just move that. Okay. So the talk today, I'll be providing the first talk to give some context on the Arctic and why it's a unique environment for deploying solar photovoltaics. And this is related to a report that we recently published in February of 2026. So I'm Erin Tanita. I'm a physical scientist with CanMet Energy in Ottawa, Canada. And I'll focus on two things in this webinar today: what defines the Arctic from an energy and environmental perspective, and how meteorological conditions fundamentally shape and influence PV behavior at high latitudes. But before I dive into that, I'd like to acknowledge that this report was a very large effort. So we have, I think, 16 authors representing 6 different countries located in high latitudes. So it really was a large group effort from a lot of passionate researchers. Okay, so let's get into the Arctic now. So the Greater Arctic region, or the Circumpolar North, kind of just more simply we'll refer to this as the Arctic. And we define this as above 60 degrees north latitude in our report. There's a number of different ways of defining the Arctic region, but we use this latitude boundary for simplicity here. And although the region contains diverse climates, cultures, and governance structures, it shares several defining characteristics. So notably low population density, extreme seasonality, and exposure to permafrost, snowfall, and climate change. As was mentioned, more than 17 million people live above 60 degrees north, spread across a vast land area representing 13% of Earth's surface. And this makes the Arctic one of the least densely populated, yet most infrastructure intensive regions on the planet. Importantly, there are two fundamentally different Arctic electricity paradigms. So we have grid-connected regions, such as the Nordic countries and parts of Russia, and these are regions that are integrated into national or multinational grids that have been historically dominated by hydro, nuclear, and wind energy. We then have our second electricity paradigm, which is isolated microgrid communities. So there are hundreds of communities in Alaska, northern Canada, Greenland, and portions of Russia that all rely on isolated microgrids for energy. And these are historically dominated by diesel fuel for their electricity and heating. So these two paradigms face the same environment, but very different technical and economic realities, which is why Arctic PV performance and value can't really be generalized. We'll be doing our best to make some generalizations and provide some background information in these talks today. But really, when it comes to having detailed plans for solar photovoltaics, it will be done on kind of a community by community or regional basis. So energy in the Arctic is fundamentally about security and resilience, not just decarbonization. So across much of the circumpolar north, particularly in these remote communities in Alaska, northern Canada, and Greenland, energy systems rely heavily on imported diesel, which is transported by seasonal barge over ice roads or on aircraft at enormous cost. So in many Arctic communities, electricity prices can be 3 to 10 times higher than national averages. And fuel supply interruptions can threaten essential services like health services, water treatment, and telecommunications. You can see an example of an ice road in northern Canada here. Climate change is also intensifying the vulnerability. So the Arctic is warming at 2 to 4 times faster than the global average, which is destabilizing ice roads, eroding coastlines, and increasing the frequency of infrastructure failures across energy systems in the Arctic. But despite these challenges, the Arctic is a global innovation hotspot for microgrids and hybrid energy systems. So, Arctic communities are often amongst the first to deploy high renewable penetration grids, also doing more innovation into hybrid energy systems and advanced battery controls. Importantly, many renewable projects in these communities are also community driven and can be linked to the goals and drive Indigenous self-determination and energy sovereignty. But why solar PV? Why are we talking about solar energy today? Why is this interesting in the Arctic? Well, costs have dropped dramatically for solar PV modules in the past decade, which now opens up the possibility for deployment in these extreme remote environments. So PV in the Arctic, well, it's not going to be displacing fossil fuels over winter months largely, but there's a lot of potential over the summer. And using the PV to displace diesel in the summer can additionally reduce environmental risks from fossil fuel. It also has the added benefit of diversifying the electricity mix, which can help stabilize electricity prices. And PV is also modular and scalable, which makes it suitable for deploying on a small community scale as needed or on a large utility scale as needed. So it can be very nice for designing in remote communities, which maybe have 100 people. You can then design your PV array to be suitable for that population. Increasingly, northern PV projects can also be used to support Indigenous energy sovereignty. They can be used to build local technical capacity and enable community ownership and reduce exposure to volatile fuel markets. So we are indeed seeing rapid growth across Arctic countries in the deployment of solar PV. So in Canada and Alaska in particular, we're seeing a lot of growth in community scale PV projects. We're also seeing more deployments and planned deployments of utility scale in Nordic countries and seeing annual growth rates that can be as high as 50 to 150% per year in some Arctic regions. So to understand what PV can contribute, we need to look a little more closely into the environment itself. So this is a busy figure here, but looking at the annual irradiance trends globally, we can see as a function of latitude that there's a clear decline in annual irradiance as we move to higher latitudes. So this figure here, we're looking at global horizontal irradiance, direct normal irradiance, and diffuse horizontal irradiance. And the Arctic is clearly sitting at the lower end of annual totals. Interestingly, we also saw this kind of two separate regimes in this mid-latitude locations. And those clusters represent dry versus humid climates. And it's a reminder that latitude is not the main driver alone. We also need to look at the specific atmospheric conditions of the sites as well. So annual totals only tell us a part of the story. We also need to understand how irradiance is distributed throughout the year. And this is very interesting in the Arctic. So one of the defining features is extreme seasonality. So above the Arctic Circle, there's no sunlight at all at the winter solstice. So you'll have a 24-hour of nighttime. You can see here, this is a GIF of an Alaskan community in the wintertime where the sun just rises and sets. So you can imagine above the Arctic Circle, you might get a little bit of brightening on the horizon, but never see the sun for some days. On the other side of the story, at the summer solstice above the Arctic Circle, the sun will not set at all. So you can see this GIF here made by the BBC of an Arctic location in the summertime. So the sun sort of bobs up and down as it sweeps a 360-degree around the horizon. Looking in more scientific detail here, this shows distribution of global horizontal irradiance throughout the months of the year and hours of the day. So you can see in a lower latitude location, there's not much in terms of seasonal effects. The day length in the wintertime is pretty similar to the summertime. But as we move across into higher latitudes, we can see how dramatically daylight availability increases in the summer so that you end up with 24 hours of sunshine and diminishes in the winter to having no sunshine at all for some winter months. So this creates a system where nearly all PV production occurs over a short seasonal window. And this motivates why storage, hybridization, and system design choices really matter in Arctic PV systems. So solar energy will not be a year-round baseload, but it can act as a strategical seasonal resource. So at high latitudes, we tend to see that the sun remains lower on the horizon, even during summer months. You can see here, these are plots of the solar path for in solid here. This is a 65 degrees north location. And then the dashed lines here are 35 degrees north. Plotting the solar elevation angle versus the azimuth. So like we saw in that last GIF in the sunshine, in the summer, lots of sunshine, you'll see around the summer solstice that the sun won't really set. At the 65 degrees north location, we just set for a little bit of time, but it's over that wide range of azimuth angles. We also see lower solar elevation than what we would get in a more mid-latitude location. What's really interesting about the solar path when it comes to PV system design is that traditionally in the Northern Hemisphere, we would deploy fixed tilt PV systems to face south to maximize annual energy yield. But in an Arctic location, for many hours of the day, the sun will actually be behind a south-facing array. So this challenges traditional assumptions for how we make deployments in Arctic regions and motivates different designs, such as vertical systems, bifacial systems, and ones that faced east-west. So these geometrical differences are the core reason why Arctic PV design will often diverge from low or mid-latitude best practices. As we move to higher latitudes, the diffuse fraction of irradiance also increases. You can see that here. So diffuse fraction is the diffuse horizontal irradiance divided by global horizontal irradiance. This is largely due to increase in cloudiness with latitude. Um, Lower solar elevation angles also means that we have higher air mass. So air mass here quantifies the path length of sunlight through the atmosphere, normalized to if the sun was directly overhead. So that's the minimum amount of atmosphere that the sunlight will have to traverse to hit the ground. But because we have lower solar elevation angles, for much of the year, the sun is quite a bit closer to the horizon. And this shifts the spectrum of light to having more of a red shift and less UV light, which is easy to observe. At sunset, you'll notice that the sun becomes more orange and red in color. And this actually boosts silicon PV cell efficiency. And as a result, Arctic PV systems often end up operating under conditions that are different from standard rated assumptions that were built and developed with lower latitude locations in mind. So the key takeaway here is that Arctic PV is not simply about less sun, it is also different sun. So not too surprising, Arctic temperatures are consistently lower throughout the year. So for example, this shows monthly average temperatures, and the blue bars here are Fairbanks, and you'll see that reaches annual or monthly averages as low as -20 in the winter to +15 in the summer, versus the location like Mexico City. There's a little bit of variation with the months, but it's not nearly as dramatic. PV system components must also regularly survive -40 degrees Celsius conditions or even lower. So they must be designed for these extreme temperatures, which can impose stricter requirements on the materials of PV systems. There's also a strong positive correlation between lower irradiance and cooler temperatures. So this means PV systems often operate at lower temperatures when they are producing power. So this figure here shows the distribution of daylight hours binned by ambient temperature and global irradiance. So you'll see in Mexico City that for much of the year, you produce most of your energy at these higher radiance conditions, and at temperatures between +20 and +30, versus for mid-latitudes and high latitudes, you have much wider distribution of conditions where your daylight falls. So in Fairbanks, temperatures can be -30, but you don't actually have too much irradiance that occurs under those conditions. Most typically, you'll have your irradiance falling when it's between -10 and +20 degrees Celsius. And what is a common misconception is that lower operating temperatures actually lead to higher PV cell efficiency and higher voltage. They can also have the benefit of suppressing certain temperature-driven degradation mechanisms. So as a result, cold climates can partially offset the reduced irradiance with enhanced performance when the sun is available. Now, of course, we can't talk about the Arctic without talking about snow. So snow can introduce both challenges and opportunities for solar PV deployments. So it can accumulate on panels and block light, which will then reduce the power production of the PV plant. But it can also accumulate on the ground, which will increase the albedo or the reflectance of the ground, which then increases the power production of solar panels. So you'll see on these plotted figures here the days per year with snow and maximum snow depth. So in many Arctic communities, many high latitude locations, there's over 200 days of snow per year, and the snow depth can be as high as 1 to 2 meters. Now, permafrost is also a notable condition of these regions. And permafrost is the ground soil that has remained frozen for at least 2 consecutive years. But in many cases, this permafrost has actually been frozen for hundreds and thousands of years. And you can see the image here shows different permafrost regions above 50 degrees north. So in Arctic, we really need to consider permafrost effects, and this can have major implications for your PV foundation design and construction practices, which Josh will touch on a little bit more in the final talk of the webinar today. So one final note here about snow is that there can be some challenges in the data. So you'll see plotted here the average albedo as a function of latitude and the percent of year with snow coverage. So interestingly, you'll see snow coverage above 60% in many locations. But you might also note some weird effects, such as this cluster of data at 0.2 albedo here. So many weather data sets that are used in PV models can contain data artifacts and inaccurate assumptions for northern regions. So when data is missing, you might infill with an assumption that's reasonable for a lower latitude location, but doesn't apply to a high latitude location. So often albedo is set to 0.2 as a default, which roughly represents like a green grass. But this is not going to be accurate in an Arctic location where 60% of the year there's snow on the ground. So we need to keep in mind that these weather data sets still need to evolve, and further research is needed to make the data better for Arctic environments. So this leads me to the final slide of my talk today with some key takeaways that are summarized here. So the Arctic is a distinct operating environment with extreme seasonality that defines the PV production. It can provide fuel savings and resilience and risk reduction through many Arctic regions. We also see that sunlight is notably different in Arctic regions. Temperatures are cooler, and snow and permafrost are a regular part of the operating environment. So successful Arctic PV deployment depends on maximizing, or sorry, doesn't depend on maximizing annual energy yield as much as it depends on context-aware design and creating a system that will be resilient to extreme weather. So with this in mind, that's the end of this presentation. I'll invite everyone to ask any questions you have related to this in the Q&A, and I'll go in and type some responses and respond verbally at the end as well. So I'll then pass it off for the next presentation, which will dive deeper into solar resource.
Yes, thank you very much, Erin, for this part one. And while you are getting prepared for the second presentation on solar resource and irradiance data in the Arctic, which was prepared by our second speaker, Adam Jensen, I just give some introduction. Also, Erin, you will present his slides. So Adam, who is also part of the author team for preparing this report. He graduated from Technical University in Denmark, where he is currently employed as an associate professor, and he's leading research in solar resource assessment, focusing on measuring and modeling irradiance in different PV applications. Having said this, I again would like to give you the floor, Erin, to also present Adam's slides. He will join us for the discussion later.
Yeah, so for some technical difficulties, I'll be presenting on behalf of Adam today. And this presentation will focus on solar resource data, which underpins everything related to PV design, performance assessment, and financing. So today we'll talk more about how confident we actually are in solar resource data north of 60 degrees. So reliable irradiance data is crucial for designing and financing new PV plants, as well as operating large-scale systems. But the Arctic is perhaps one of the most challenging environments for collecting irradiance data, both measuring it on the ground or creating models for how the irradiance performs. So you'll see an image here of a pyranometer that has some snow on it. So that'll be a common theme in one of the challenges of Arctic measurements of solar irradiance. So there's extreme cold, snow and frost that can build up on sensors, and low sun angles. And these conditions all make it extra challenging for solar irradiance measurements. So ground measurements remain the gold standard for solar resource assessment, but they can be quite hard to maintain in high latitude climates. So snow, ice, and rime can build up quite quickly on instruments, which will degrade their accuracy if the sensors are not being actively heated. So you'll see a photo here, and this is a setup in Copenhagen, Denmark, of many different pyranometers that measure global horizontal irradiance. So these represent very common brands that are used, Kippenzonen, Echo, Husqvarna, and more. So you can see there's very significant differences in the heating capabilities of these sensors, with some that are completely covered by snow. You'll also see on the right-hand side here, this is a solar tracker with several pyroheliometers that are mounted to measure the direct sunlight from the circumsolar region of the sun. And you'll see even though they have sort of these caps over the sensors, the snow can find a way to make its way and block that sensor from taking accurate measurements. So in experiences from Arctic and subarctic stations around the world, we're seeing that heated sensors are essential. So the heating can either be provided internally or externally. But with new instrument technology developments, new digital sensors, now internal heating is the standard. Without heating, winter data can be biased too low, or it could be entirely unusable. Multi-component measurement stations, so that's stations that measure diffuse, direct, and global irradiance, are very rare in the Arctic. So you'll see here a plot of different high-quality stations in the Arctic with their status indicated by the color. Many historical stations have been retired, lost funding, or experienced repeated mechanical failure, and few stations provide publicly available data. We've also had instances of stations having problems, such as at the Summit station in Greenland, where the solar tracker often does not work due to the harsh conditions. So that means you'll have large data gaps for many months of the year while the solar tracker is not tracking the sun. And that's a common issue. So solar trackers are particularly vulnerable to freezing, high wind conditions, and ice accumulation. And as a result of that challenging environment to operate in, this means we have very limited direct and diffuse measurements north of 60 degrees. And this limits our ability to validate and improve satellite irradiance products and to better understand bifacial gain and PV performance in these regions. So satellite-derived irradiance is normally the preferred source of modeled data. So you'll see plotted here, these are geostationary satellites, and they sit above the equator. This means they have very shallow viewing angles of high latitude locations, poor spatial resolution, and atmospheric path length distortions. So at 60 to 65 degrees north, that's roughly where traditional geostationary satellite products become increasingly unreliable. Snow can often be misclassified as clouds, for example, and that can lead to systematic underestimation of your irradiance. These often, these limitations of these satellite products often force Arctic or high latitude users to rely on lower accuracy data sets. So reanalysis is known to have significantly larger uncertainties than satellite-derived irradiance, but it ends up being commonly used in the Arctic due to the limitations of that satellite viewing angle that I mentioned. So ERA5 is a very commonly used global reanalysis model. Its strengths are that it has a very long historical record going back to 1940 up till present. It has temporal consistency and it's very easy to access via website or PVLib and other modeling tools. Um, However, this is a reanalysis model, so it does not directly observe irradiance. It infers solar radiation through atmospheric models, which are less constrained at high latitudes and weaker because there's less observational data on the ground to help support the model development. So as a result, uncertainties can be quite a lot higher in high latitude regions, and they can have location-specific biases. So Error 5 often is used as more of a fallback option rather than the best case scenario data set. NASA Power is another data product that is commonly used in high latitude locations. It has some satellite-based input and covers a period of 2001 onwards. So it can be used for studies such as looking at interannual irradiance variability, but the spatial resolution is a limiting factor. So it provides a spatial resolution of 1 degree by 1 degree, which is roughly 110 kilometers on a grid. And this is much coarser than your typical satellite-derived data set. So it won't be able to capture effects accurately over mountainous regions if there's a strong gradient in elevation or along the coast, for example. Again, it's also easy to access via website, API, or PVLib. Now, recently, this is very exciting, NREL, or the National Laboratory of the Rockies, recently developed a polar model. The NSRDB has just released in late 2025 a polar model that covers above 60 degrees north, and it represents a major step forward for Arctic solar resource assessment. So it relies on polar orbiting satellites, which can provide a much better viewing geometry at high latitudes and an orders of magnitude improvement in spatial resolution. So you'll see the spatial resolution of this data set is 4 kilometers compared to the 110 kilometers of NASA Power. So what it does is it's using images that are taken by NASA's polar orbiting satellites, such as the instrument, the Moderate Resolution Imaging Spectrometer, or MODIS, if you've heard of that, that are on Aqua and Terra platforms. So this is a fun GIF showing hourly the irradiance in July over the 60 degrees north region. So at the 4 kilometer resolution, we can now capture terrain and coastal effects that might be missed by other data sets. And this data set is now being validated against the existing ground station measurement data that we do have in the Arctic. But it's still an important and ongoing effort that'll help us better understand the accuracy of this polar tailored model. So in a little more detail here, zooming into Alaska, this is that same NSRDB polar data. And you can see a wide variety of irradiance conditions throughout the state of Alaska. So within Alaska, you can get an irradiance of 2 kilowatt hours per meter squared per day, compared to in this more southern region, you might have as high as 3.5 kilowatt hours per meter squared per day. And these gradients are much more difficult to see and resolve in those coarser data sets. So this has important implications for project siting, comparative analysis, and regional planning. So main takeaway here is that Arctic solar irradiance is highly local, and we really need this high resolution data to do our research. So for further information, you're invited to take a look at the Best Practices Handbook published by IEA PVPS Task 16. So this provides some nice guidance on solar irradiance models, data sets, and measurement best practices. And for Arctic applications, following these guidelines is especially critical for getting high enough quality data in these regions. So that brings me to the end of Adam's talk today. I'll just say that the key takeaway is that solar resource uncertainty is one of the defining challenges of the Arctic region. And that challenge is currently being reduced but not eliminated by improved instrumentation, so having more internal heating options on the market and new satellite data products being developed as well, such as the NSRDB polar model. So understanding the strengths and weaknesses of each of these instruments, as well as data products, is essential for creating credible Arctic data and for improving project bankability. So thank you, and I invite you to ask any questions you have in the Q&A, and Adam will be able to respond there. So, thanks.
Thank you again, Erin, for your second presentation on solar resource. And as you said, we will have time to discuss your questions in the Q&A and also other questions at the end of the session. But now we are coming to our third presentation on design and modeling, but also looking at the performance in very cold climates. And I would like to introduce Joshua Stein. He works at Sandia National Laboratory since 2001. He is doing research in PV since 2009. Josh is the world leader in PV performance modeling, and he is also the founder of the PV Performance Modeling Collaborative, PVPMC, and leads related projects to bifacial PV and also PV module and system design. And we're interested and looking forward to your presentation now on the Arctic region and specifics.
Thank you, Ulrike, and thank you, Erin. Erin, you gave a great introduction and you're a hard act to follow, so I'll do my best. But I'm going to focus on kind of taking from what Erin was talking about the unique characteristics and the challenges in the inputs to these solar systems, and talk a little bit about how we build these systems to maximize this environment. So this is kind of sort of the design and modeling considerations, and then we'll look at also some other aspects later. So one of the things that you learn pretty quickly when you start thinking about Arctic PV systems is that most of them up to this point, although this is changing, are pretty small, small systems, and there's a wide range in the design configurations. You can see, as Erin was talking about, in the summer months, the sun is very low elevation angle. So there's been communities like in Fairbanks where they've tried these kind of orientations that try to follow the sun. You can imagine from an electrical configuration that could be quite introduce a lot of mismatch. So there's lots of challenges. Um, there's also early on some systems tried to use two-axis trackers, because you'd think with that amount of variability that you would benefit from being able to sort of point your modules at the sun all the time, and a two-axis tracker can do that. What they found is that, as Erin mentioned, is that the reliability of moving parts in a very harsh climate and the O&M response really has moved design companies away from doing tracking in the Arctic. I mean, that's not to say that there are some single axis trackers. You can see a system here in B in Norway, and especially in the Nordic region in Europe, there are putting in a lot of larger single axis tracking systems. Most systems are fixed tilt, and might think that you would follow kind of the rule of thumb of putting a fixed tilt facing the equator at a latitude tilt. In fact, as Erin mentioned, with the high diffuse fraction, there's actually a push to making systems a little less tilted, because there's a lot of times of the year where it's not sunny, a sunny day. It'll be more diffuse, and so therefore you might want to face your modules a little bit towards the sky. But then there's also this big push more recently of, since there's snow on the ground for quite a long time, or many months of the year, having a east-west vertical system takes advantage of the reflection from the snow. It also has a really good match with the amount of when that energy is produced. So instead you get most of your energy at sort of the morning and the evening rather than at midday, and that tends to match load profiles in many communities. And then there's also interest about building integrated There are many challenges with rooftop systems, with clearing of snow. It's actually there's a public safety issue here too, with snow falling on people or people going up on roofs and trying to remove the snow. And there's many instances in Arctic communities where people are injured or even killed by maintaining their PV system. So there's a lot of interest there. So some of the things, just to kind of from that kind of list of things, fixed tilt tends to be preferred. It's simpler, it's more reliable. Um, Tracking systems really have reliability issues, but I think there are companies that are trying to build specialized equipment that can handle that. But there's still kind of a tension there. You do need to have larger row spacing due to the low solar elevation angles. So you get much more, so your ground coverage ratios are going to be much more, much lower in Arctic areas. You also have to have the panels mounted higher to account for snow shedding. And you want to allow the snow to actually fall on the ground and not block the lower portion of the array. There's a big interest in using snow fences around various fields, and I'll talk a little bit about this a little bit more detail, but there's a lot of snow drifting in areas where you have all these PV arrays, and so you need to account for that. So there's a lot of design considerations about building snow fences. Bifacial modules, I mean, are pretty much standard conventional PV that you can get. It's really hard to find monofacial modules, and that's actually a good thing especially for Arctic environments where the snow is on the ground for a long time. And so there's a lot of uncertainty here in terms of like what the albedo will be over time. Snow albedo is not uniform and constant. It changes over time. So is a bunch of uncertainty with that. And vertical east-west bifacial systems are really, there's a lot of interest now in those for the reasons I mentioned before. So here's just an example of these vertical bifacial systems. You saw the system that we visited in Sweden that is on the cover of the report, but there are other types of systems that are being developed. And as Aaron mentioned, this is a real example of the innovation that's happening in these climates. There's really innovative solutions. And so these are sort of half panels. So they're very long and not very high, and you can therefore pack them a little densely on a rooftop. And also they are more resistant to wind loads. And so this is just an example of some interesting and it's also easier to I guess I'm not exactly sure how they deal with the snow melting here, but there's these also benefit from having snow in between them because you can then get the reflections. Let's see. So there was a question in the chat that I want to address. When somebody asked, why is it that if the sun is at its maximum elevation in the south, if you're in the northern hemisphere at noon, why would you want to put modules facing east-west? And I think the answer here, I mean, we can look at this through doing some modeling and comparisons, but essentially, yes, if you have a sunny day and you're pointing your array to the south, you're going to have your sort of maximum power at that point at solar noon. But really, arrays are not designed for maximum power. They're more designed for maximum energy typically. And so this is a kind of two different sets of plots. One is, if you remember, Aaron showed the effects on irradiance components at for different components as a function of latitude. And this basically shows that if you start orienting your arrays, we're now focused on plane of array irradiance or insolation. And so if you look at cumulative plane of array insolation for three different climates. So the red are in Phoenix, the green lines are in Ottawa at 45 degrees north, and the blue is from Fairbanks. And this is using TMY data from those locations. So it includes, the effects of clouds and other things. You can see that the cumulative irradiance in these locations is lower, as Aaron pointed out, but that if you include bifacial, which is in the solid lines, you get a little bit of a boost for the single axis tracking and the south fixed tilt at latitude. And the east-west bifacial assumes that we have that already. It's all bifacial, right? So, and then if you take those plane of array irradiance measurements and you start to put them into an actual PV performance model, it's interesting in that you can see, for instance, in Fairbanks, if the dotted line here, this is cumulative power out of a system with various orientations and whether monofacial or bifacial. One thing you can notice is that the difference in the blue lines is much greater than the difference in the red lines, which is in Charlotte. So the effect, this is basically saying that the effect of bifacial and also of the effect of having a bifacial is much higher in northern climates due to the snow. And the other thing to keep in mind here is that the solid blue line, which is a latitude tilt, let's see, latitude tilt bifacial versus the vertical east-west bifacial, that these are, you do get a little bit more energy in this case with a latitude tilt bifacial, but the vertical has some benefits. And these calculations did not include snow coverage or anything like that. So while there is a little bit of a difference theoretically, in practice, these lines tend to we think that they're going to be much closer to each other. And I think it's also interesting to note that while even though we have lower irradiance, that by putting these modules in various orientations, you can get performance that's even higher than in Charlotte with monofacial if you use bifacial up in an Arctic region. So one thing we didn't mention before is that we can use models to figure out kind of and predict what's going to happen. The real limitation, and one of the things that I think we're going to be hoping to help find, is working with some of the installers in these environments and trying to get some real validated field data going forward. So that if anybody, it might seem easy to do, but there's lots of data restrictions, and so we'll be working hopefully in the future to try to actually get real measurements from these systems so we can have validated models. All right. A lot of these are some kind of the summary of some of the challenges, and some of them we've talked about already. There's definitely higher uncertainty due to limited data and model validation above in this greater Arctic region. We have increased error for cloudy conditions and high albedo environments. There's how do you deal with albedo changing over time and things like that. There's less validated models for vertical and facade systems. So there's a lot of work to be done as more PV gets into the Arctic to better understand and constrain them. And then, as Aaron mentioned, there's also challenges with even designs and bringing things in, just with transportation and shipping and things like that. So want to move on quickly. This was mentioned also before about PV performance in cold temperatures. I wanted to mention a few other things. So it's pretty clear that if you look at PV modules, that they have a negative temperature coefficient, meaning that they will perform worse at higher temperatures, but that also means they perform better at lower temperatures. This is typically manifested in a higher voltage. So at colder temperatures, you need a higher voltage. You get a higher voltage and a slightly lower current. Um, it really depends on your cell technology. So, while in some climates you might look for a module with a low temperature coefficient. In the Arctic, if you have really cold temperatures, you may favor a module that has a slightly higher temperature coefficient. So anyway, there's interesting things about that. There's um, also the effect of low sun angles means that you have more red light typically and you can get that will have a factor on um, your quantum efficiency of your cell. And so there's a little bit of a benefit with silicon solar cells to having that more redder light. I think we talked a little bit about this already. So this is just basically saying that in many of these places, we're operating at lower temperatures and even lower temperatures than the standard test conditions. So you need to be able to translate the conditions at your site to the performance. So I want to move on a little bit to the challenges of actually deploying these systems in frozen soils and permafrost. Um, there is something that like not many people talk about when you study solar energy. You're mostly focused on how the solar cells perform, but it turns out that to make a system economic, you really have to make sure that it will be um, attached to the ground or to your buildings, but typically ground mount systems in a way that the system's not going to move or get damaged. And so one thing about permafrost is that it comes kind of like snow. It comes in many different forms, but there are types of permafrost that typically or commonly permafrost has very high water content. There's a type called Yedema that's happens kind of it's distributed around in Arctic areas that's very high water content. So when those permafrosts actually melt, or even at the top layers, the ground becomes very unstable. And so it's in many cases when you're building infrastructure in permafrost regions, you are trying to prevent deep thawing of the ground seasonally. It's better to keep the ground frozen as much as possible, um, and restrict that active layer to pretty shallow depths. And so there's a bunch of uh, evidence that we collected from like looking around the world, where there's a whole bunch of evidence of PV systems and piles being moved due to frost heaves and um, being disturbing the arrays and causing damage. So, like I said, another complication here, if you want to keep your ground frozen, if you're building on permafrost, first of all, one thing you would do is you would install your piles deeper. And so in many Arctic regions, we try to bring things very, very deep. Um, the other thing is that the active layer in the summertime is affected by actually what your winter conditions are. And so one of the things that this is a system that was in Fairbanks that they did some interesting measurements on in Kotzebue, Alaska. And the arrays actually caused drifting and different snow depths. And what happens is that in the wintertime is the time when the ground actually refreezes. And if the array creates a snow drift, typically behind the array or in front of the array from falling snow, that can act as an insulator, causing that the ground doesn't freeze as much in those areas versus, say, right beneath the array where it may freeze more. And that kind of effect has been measured. This is some ground temperature measurements around a solar array that were made in Alaska. And you can see kind of the um, differences can get quite large at all the way down to, these are in feet, down to like 4 feet of depth. So that's, and what they found is that insulating factors were actually causing the ground to thaw deeper and cause instabilities. So Aaron mentioned this as well. There's very little data about degradation rates in cold climates, but we collected all of the papers that we could find. These were about 16 studies that were looked at degradation rates, and so it's a small sample statistics, but we found that the uh, the standard sort of continental degradation rate averages about 0.75 percent per degree C, or sorry, percent per year of degradation rate, but that the average and the medians were significantly lower than that. I think this remains to be seen in terms of whether degradation rates are in fact lower. They may just be different. Um, so part of this is interesting to there are different stresses on PV modules and arrays in Arctic regions. One of them is snow loading, and that can cause differential stress on modules. And so you can see this is just kind of a concept showing that you can get excessive ice buildup and snow loads on the south or the bottom part of your module, which can then lead to uneven loading. And so the other thing is that there's snow is actually forms on it's forms in the atmosphere with water droplets that usually nucleate on dust particles. And so snow, if you've ever melted snow to drink for water, it's always very dirty water. So when it melts and leaves that dirt on the module surface, you can get a lot of soiling effects as well. So there's a lot of complicated interactions. Um, leading One of the interesting things that's come out recently was this new IEC standard for non-uniform snow load testing. That was IEC 62938, which is I think it's a good indication that people are starting to think about this in the standards community. Um, the other interesting thing is that of what type of encapsulant you use in your module. And a capsulant's purpose is to kind of hold the module together. It holds the glass to the cells and it keeps everything together and isolated from the environment. But the materials that they use, the most common typically has been EVA. It actually has a glass transition temperature about minus 15 degrees C, which is definitely a temperature that these modules will reach. And that means that at temperatures below minus 15 degrees, the material properties of that becomes very rigid. And so if you then unevenly load those modules, you can transfer stress of that loading to the cell and cause cell breakage. And so there are other encapsulants. So if you're thinking about building a module or having modules, you may want to look into what encapsulants are being used and try to favor one that has a lower glass transition temperature. So POEs and PDMS encapsulants have much lower glass transition temperatures and therefore will be less likely to transfer that uneven stress to the cells. There's also interesting solutions for mitigating snow mitigation. I think this is pretty much the end of my talk, but there's passive solutions. People are doing investigations on ice-phobic and hydrophobic coatings. I think this is a low TRL level activity. Many of these coatings will work, but you have to reapply them time and time again, and that may not be economically feasible. But definitely having steeper angles for gravity shedding, installing snow fences, having frameless modules that can reduce ice buildup at the edge is a strategy, although those are not as common. And then system layout optimization, just planning for snow to fall off of surfaces. There is some active research going on in active solutions. There are there's research in Japan where they're looking at actively surface heating or using resistive wires at the edge of the modules to encourage snow to fall off. Um, there are a variety of machines and kind of methods that people are trying to develop that can mechanically remove the snow without breaking modules and it help actually it's really important, especially for rooftop systems. There are concerns about chemical treatments in terms of environmental stuff. Um, but all these active solutions, they definitely require external power, and they're going to you have to weigh the power and the risks of these active solutions against just passive solutions. So that's the end of my slides. Stop my share. Thank you.
Yes. Thank you very
Yeah.
much, Josh and Erin, for your very comprehensive presentations. I think a lot of material, and we also see several questions. I would like to address the first one on irradiance to Adam. And the question is about what is the explanation for high irradiation differences between different regions of Alaska? Is it the latitude or are there other factors? And the question was put by Mario Lehmann. Adam, would you like to answer this question, please?
Yes. So particularly for Alaska, that definitely, with all the Arctics, it's a latitude thing, but Alaska has some very coastal clouds coming in that creates a lot of these changes. Um, and also what's really unique is the mountains, and the mountains can sometimes be blocking these clouds. So you can really have sort of two regions that are very close to each other, but on different sides of the mountains that can have very different cloud patterns. That's particularly why this NSODB polar data set with its 4 kilometer resolution is kind of a game changer in this region.
Yeah, thank you. The second question maybe for Josh on your east-west orientation. So the question was by Anonymous. There was a simulation presented by you, Josh, on the bifacial modules with east-west configuration. What level of bifaciality was assumed in this case? So could you explore more
Yeah.
this?
So I think I'd have to double check it. I think that is explained in the report, but I think I assumed an 80% bifaciality, kind of a moderate. I'd have to look and double check that, but it is in the report. It's typically bifaciality is either between 80 and 90%, and it can even get above 90% for some heterojunction cells. So yeah.
Okay, we will follow this up. There was a question on modeling. I don't know who would like to take this by Roberta. Is there any energy model that accounts for energy gain due to snow reflectance?
I can speak to that.
Yeah.
Yeah, there are a number of different PV models that have been developed for the specifically bifacial panels. So there's a lot of active research and development into validating these models. So there's more complex ones like ray tracing, or more simplified ones which use view factor approaches. But yeah, it's really about adapting these models that were originally designed just for monofacial panels. So they were calculating irradiance transposition onto the front face. Well, now we need to add in an extra step to calculate onto the rear as well. So a lot of the mathematical framework is built up already, but it's just about starting to look at the rear face, which can have added complications. For example, you'd have beams of metal to support the panels, and you need to take that into consideration to get accurate results, as well as making sure you have accurate data for what your ground conditions are. So it's really opened up a whole a whole world of research into modeling and improving the accuracy of models. But I would say most models these days have the option for bifacial systems just because they're what's prevalent on the market now. So the models have had to catch up. But still a lot of research being done on improving those models for the unique conditions of bifacial panels.
Yeah, I might add there's also I agree, there's a lot of really sophisticated modeling that can be done. One of the challenges though is what do you put as input for those models? Because by albedo can vary over time, even with snow, like with snow, it varies with time. Fresh snow has very high albedo, old snow is much lower. And then as the snow melts, you can have spatially distributed, you can have patches of snowdrifts that can hang around for weeks to months potentially, especially if there's, drifts and things like that. So
Okay, thanks. One other question is directed to degradation of the solar cell in the snow field. I think, Josh, you had some examples also on degradation rates. This is a very general question, but maybe you can answer.
yeah, I think degradation rates in general are quite variable and quite uncertain because there's a lot. I mean, even a PV cell, there are many different technologies for PV cells, and the degradation mechanisms are very complicated. So I would point people to some of the reports that are the IEA Task 13 has put out on this topic. We have some pretty complete reports on what's known about these. As for the cold climate or the Arctic degradation modes, it's even more uncertain. And so the data that I did show is very sparse and should be taken as what we were able to find. But I think as we get more PV systems deployed and more experience and learning more about how they fail or how they degrade, we will be able to report out later, hopefully.
Yes. And on the general degradation rates for systems in cold, but also other climates, we have published 2 reports, and one of them was also on the performance loss rate, where we compared the performance loss rate to the degradation rate, and that was published, I think, at the end of 2024. So just feel free to go back to the Task 13 website to look for these 2 reports. There is one interesting question, how PV modules which are using or generating electricity, and how to use part of this energy to heat cables on the surface of the panels, similar to rear window defrosters in the car. Is this an option, and do you have experiences with using the PV electricity for heating the cables in the PV?
I can comment a little bit. I don't know if Aaron, if you have something to add, but typically with PV systems, adding more complexity is typically not economically um, expedient. And the other thing too about that's actually hard about this solution is that many times the modules are made by a manufacturer and they have a warranty. And in order to actually do something to those modules, like heat them or add other things on top of them, very likely will void warranties. So it's both a technical problem, but also a commercial problem. So I think most of the examples of actually adding heating elements are done in sort of a research environment, not in a commercial environment for these reasons.
Yeah. But I recall, I think also in northern Sweden, we have seen a plant which was heated in order to make the snow slide away, just to
Yeah.
use this energy to melt just the surface in order to make sure that the snow which was covering the whole panels
Yeah.
is sliding
So
down.
you can also do, I mean, you can actually use the inverter, a grid connected inverter to back bias the array. And that will actually generate heat within the cells themselves. There are concerns there about warranty issues and things. So there are ideas, but it ends up, yeah. Well, I think we just need more data and more information to see whether those methods don't have any harmful effects on the reliability of the system in the long term.
Clear. I would like to come back to a question which was already answered by Josh, and this question was why not use hybrid systems, wind and solar? And the additional question was that he actually was thinking of geothermal heat, but then later he has seen that the region does not have any permeable rock. So this is not an option. Is this correct?
I think, I mean, I think it depends where you are. I mean, Iceland is definitely has plenty of geothermal. I think there are geothermal resources in the Arctic, that's for sure. And even there's different grades of geothermal, right? You can have high temperature geothermal, but there's also ground source heat pumps and things like that. Um, uh, in terms of the wind hybrid systems, I'm not an expert in wind, but in talking to some of my colleagues who are, and wind energy is very cheap when you build it at very large scales. And it's not nearly as efficient or as cost effective at smaller scales. And so these big wind farms is where you get the real benefit of wind. That said, there are definitely wind turbines in Arctic communities. It's, I don't know, Aaron, maybe you have more experience with this.
Yeah, it's pretty popular, I'd say, for Arctic communities in Canada because we have a lot of wind resource. But there's definitely more research and development in the industry for smaller wind turbines that can service these remote communities, and also more designing and research into how to build the foundations. So we're seeing some more like ballasted system designs. Um, that could work over permafrost. Um, yeah, so it's definitely it's a viable option, but it can come with high costs, but that's sort of the reality of a lot of the energy options for remote communities. So if there's incentives to help back the upfront capital cost, then it can be worth the deployment. Especially if you're offsetting annual costs for diesel fuel. Um, yeah, so they are being deployed, definitely in Canada.
Mhm.
Maybe I can also just comment on that briefly. Really, the beauty of solar, right, is no moving parts. And that's where wind, I mean, wind certainly has a lot better load profile for, winter loads, but there's no moving parts mean you can deploy it in remote communities, and they can really operate super reliably for a long time. So in Greenland, at least where I kind of work, in my region of interest, predominantly in the Arctic, solar is really being deployed by the utility up there. Whereas wind is not really of interest too much, and particularly is Greenland also has these katabatic winds that are, super intense and often kind of will ruin some of these experimental turbines that have been there.
Yes, clear. Before coming to the mechanical reliability and our next question, I have a general question. What would you recommend for a multi-component PV ground-mounted PV system in the Arctic? How should it be configured and also maintained? For example, cleaning regimes, de-icing, tilt, and ventilation in order to ensure a maximum yield. Maybe Erin, you can start.
Sure, yeah. So that's one thing I'm working on in collaboration with Polar Knowledge Canada. We're working on setting up a high quality multi-component station at the Canadian High Arctic Research Station. And it's a very interesting environment to try and develop these multi-component measurements because, like you mentioned, it's critical that you have good heating for your sensors for the pyranometers and pyroheliometers. And then as well, there's new tracking technologies that are supposed to be designed for these more extreme environments. So we'll be testing one of those trackers and seeing how it performs. But one interesting point of advice that I heard from another Arctic station operator was that it can commonly have the tracker fail when you try to restart it in the spring. So if you're through your polar night, if there's no sun for several weeks, the tracker's not moving, and then when it tries to start moving again, when the sun comes back in the spring, it might just be stuck in that frozen state and it won't move and can have problems with getting started and actually getting accurate data. So some advice I received was to set the tracker to a fake location for those uh, winter weeks.
Mhm.
So for example, telling it it's in Hawaii, so it keeps moving
Mhm.
around, keeps moving and doesn't just stick in spot. There's also um, kind of blankets you can put around the solar trackers as well to kind of keep them more insulated, keep the heating of the self-heating of the components internal and keep it warmer. So that's another aspect that's being used to try and improve the reliability of these sensors. But I know, yeah, Adam has a lot of experience in operating these equipment in snowy climates too. But yeah, it's definitely a challenging environment, and you need to do regular O&M to check on the system and manually remove snow sometimes. Yeah, that's.
Thanks.
I'd
I
al-
think there are still challenges. Adam, you like to add?
yeah, just a comment. I mean, with these sensors, placement will get you really far if you do it smart. So if you place them kind of without where snowdrift can't build up, you really only need minimal heating to kind of keep snow off. But of course, if you're in a place where there's snow buildup because of if you place it on a table or something, then that'd be an issue. So at these northern stations, oftentimes you will place them on not a flat, not a flat, a table surface, but more of a like a gridded surface where the snow can kind of go through the table, and you have these smaller mounting brackets, for example. That's one thing that we do.
Okay. Yes, we still have 4 questions in the pipeline and a couple minutes left. So concerning the mechanical reliability, the key question is, how is the array height generally determined for the PV design? And I think, um, I mean, we're talking about the mounting system and the edges of the mounting structure.
I think that's pretty low. It's generally based on local historical data about snow and snow depths. If you have any other information about water content of the snow and things like that. Um, I I'm not familiar with if there's I don't think there's any standards out there. So that would be something that actually in our follow-on work with this group, we are planning another report and another set of studies on case studies. So rather than just sort of theoretical and kind of looking at the opportunities and challenges, really diving into real system data at these locations and hopefully documenting some of these lessons learned. So stay
Okay.
tuned for that. Yeah.
Great. So, for example, in some of the commercial design programs like PVSist, this is not a parameter which you can get out of these calculations.
No, because I mean, as many people will know, snow depth is changes just over time, even if, there's evaporation or, out of this, there's melting, there's consolidation. When
Mhm.
snow falls off, I don't know. So it's not particularly there are models that talk about, how high the snowdrift
Mhm.
will get below the modules called snow shedding models. So those you can use those to try to estimate how high you need the
Mhm.
lower edge of your array to be.
Yes.
But it really depends on a lot on the local conditions. Those models are usually empirical,
Mhm.
and it depends on where they were trained, and results may vary.
Okay. Another question is on the bifaciality and whether you know whether there are studies or reports on the energy gains from the snow on the ground, albedo effects, and how they can speed up the snow melting at the top of the modules. Are there studies on this question?
Is that like the self-heating from the backside of radiance? Aaron, I think you covered that in some of your work, didn't you?
Um, yeah, I have a general understanding. So, yeah, the bifacial energy yield gain that you can have from being over snow is quite significant. So it really depends on kind of a case by case basis, but you could see energy yield gains as high as 20% on an annual basis in an Arctic location just because you're over snow. If you were, comparing deploying a monofacial panel instead in that Arctic location. But yeah, in terms of how it can speed up snow melting on the front of a module, we kind of have an intrinsic understanding that theoretically, it seems like it should speed up the ability of the module to shed snow because it has that extra open area on the rear side that can still collect irradiance and in that produce electricity, but also generating heat at the same time. And then that extra heat can help shed the snow on the front of the panel. But there's still not entirely conclusive studies on comparing monofacial and bifacial snow shedding properties. We just sort of theorize that the bifacial panels will be better at it. But yeah, there's still more studies being done on comparing the two to really quantify and give a value about how much better they actually are. Yeah,
One clear distinction is the frame versus frameless. I mean, that there's been
that's
many
right. Yeah.
studies. So if you have frameless modules, they will shed snow more. And maybe also to add to Aaron's, like snow, even if you heat up snow that's sitting at, say, -10 degrees to -8 degrees, it's still frozen and it's still going to be pretty like strongly adhered to the module. So there's only certain conditions when you're, sort of near that melting point,
Mhm.
at the glass, snow, or ice interface where you're really going to lead to shedding.
Concerning the impact of climate change, are there projections or experiences suggesting that the snowfall could increase around Arctic regions due to the climate change?
Yeah, I'm not too familiar myself. Yeah, just generally
We
have heard that there's precipitation changes
I think it's
anticipated,
gonna
but
I think it's gonna be very locally dependent, as like kind of Adam mentioned. There's orographic effects, and so in terms of how much snow you get, I think is one of those climate model outputs that are pretty uncertain. Um, I I can post in the chat. We just actually had a paper that I was a co-author on that just got published today that looks at the effects of essentially irradiance values projections in future climates. So I can try to find the link to that and post that.
Fantastic. Thanks, Josh. And here we have a question to vertical PV installations and also in relation to agrivoltaic solutions. The author thinks that there are some synergies, like for longer row spacing, which is needed also for the farming activities to be done between these rows, and also higher installation heights. Are there comments from your part on this spacing and the um, position of these vertical PV installations compared to ground-mounted systems, and the application is for Finland?
yeah, I think we're seeing more deployment of these agri PV systems using vertical PV. Because you can imagine it's a lot easier if you have farming equipment to sort of drive it up and down these rows when they're vertical. You can plant things closer to the arrays as well. So there's a lot of synergies between the agri-PV research world and then also the Arctic research world. And you see that overlap happening in the Nordic countries in particular, where there's a lot of test systems on vertical PV with crops in between. So yeah, I think that if you have conventional ground-mounted south-facing panels in Finland, maybe you're going to get more energy yield um, out of that system on an annual basis. But from going to the east-west vertical, that's when you sort of open up. It makes it easier to implement the crops. Yeah, there's some interesting studies going on. I know of the agri-PV array in Sweden, doing some comparisons between kind of the conventional system compared to vertical. Um, yeah, so definitely can be some good synergies, like you mentioned. And yeah, the additional row spacing can help allow for more sunlight to hit the crops as well. Um, yeah, not sure if anyone else has anything to add to that, but
This does not seem to be the case, and I think we are at the end of our session, and maybe just as a concluding questions going towards the cost, and you, Aaron, mentioned why it is important to save the diesel fuel cost in isolated areas. What kind of technical and economic feasibility of high penetration PV microgrids you see in the Arctic communities? What is your expectation on the development?
yeah, so we're seeing in remote communities deployments that can offset as much as, 20 to 25% of the energy use that would normally be provided by diesel. So that can translate into tens of thousands of liters per year being saved. So that has a big economic effect. Once you can pay for, the large capital cost, the upfront cost associated with the PV panels, then you're saving that additional cost that you would pay annually for diesel. And as we're seeing that price is really fluctuating as well. So you're not as exposed to that volatile fuel market when you have these high PV penetration grids. But really, if you want to try and push beyond sort of the 20-25% variable renewables, that's where we need to have more detailed control on the microgrid, as well as having a lot more storage. So storage becomes very important if you want to have high renewable energy penetration in these small grids. And that's really why I mentioned that a lot of these communities are sort of innovation hotspots for testing out these high renewable penetration grids in an extreme environment as well. So yeah, to really kind of push beyond that 25% barrier, that's where we need more advanced controls and more battery storage, which can come with some cost as well. So there's a bit of a an
Mm.
optimization there that needs to be done. But
I might just add that it's the benefits of adding solar to a diesel grid is kind of nonlinear because, I mean, Aaron, you mentioned this about that as climate changes and we get the 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 ability to deliver the fuel at when you need it is actually becoming like narrower and narrower in time. And so it also leads to like less requirements for like diesel storage tanks, so you can like reduce your storage capacity. So there's a lot of like additional benefits that beyond just the fuel saved, like the
Yes.
infrastructure can actually be lower
Yeah.
as well.
I think this is a good point to stop the discussion here as a final word. Um, Thanks very much to all three of you for your very comprehensive presentations. I would like to mention that this team will continue working on this topic, PV in the Arctic, looking at technical issues from modeling all the way to design, but also on the economic and KPIs. And you can expect another report in the coming 2 years. And I would like to thank all participants for their active participation and questions. And again, thanks to the three of you for your presentations. And stay tuned. You will find and get our slides at the PVPS website in a couple of days to see on the results and what was presented today. So thank you very much and see you next time.